So I hope my screen is visible to all of you.
Yes, sir, it is visible, sir.
Okay, so we'll go ahead with the session. Welcome everyone to this fifth tutorial session on the course of materials characterization. Basically in the last week we were discussing about the electron lenses, what are the electrostatic lenses, what are the electromagnetic lenses, and why there are the instead of the electron beam going in a straight path, why they are diverging from their path, and why the helical path they are taking. First they are spiraling around the axis, optic axis, and then why they are spiraling. All those things we have discussed, and as well as we have discussed that how the brightness and work function of a material are one of the critical factors determining the electron gun size, which we saw. Different types of guns are there. Electron gun, one is thermionic gun, which is made up of tungsten, and another one is field electron gun, cold field electron gun, and thermal field electron gun, and Schottky field electron gun. So we touched briefly went there. In the last class we have discussed about a term called demagnification. So we will see what that I have told that the demagnification, if I am mentioning the demagnification, then it will be object size divided by uh, image size, right? That's what we have been last class we have discussed that this is the demagnification. But what is the demagnification, we need to we need to see that. Okay, this is the formula for that demagnification, but what that physically signify in an electron microscope. Magnification means we can visualize by ourselves that if we are trying to see, or we are trying to get any microscopic data from a very minute material, which is in the order of, let's say, micrometer, or in the order of nanometer. Then we since that nanometric feature we are able to see, or micrometric feature we are able to see with our naked eye, so that is what we can call it a magnification. So what do you mean by demagnification? So this, and I told that always the demagnification happens in electron microscopy, and this demagnification value is always greater than 1. So the demagnification means the electron lenses that we are using, so the beam crossover. So here is a term called beam crossover. Beam crossover means, let's say here my electron gun is there, and it is producing different electron. The electrons are extracted for, so this is, if I am talking about, this is the gun, and this is the electrons are coming, and then here I am putting my condenser lens, right? So since this condenser lens, what is the use of this condenser lens? It will put all these electrons into a focused point, or it will try to put all these electrons into a focused point. So this is what I called as the beam crossover, right? So this is what, so if I am talking that the yeah, this is my, let's say I am taking any random value, let's say this is d1. D1 is the diameter of my tip, the tungsten tip, or lab 6, or cold FEG tip. So if I am talking that this is my tip D1, then this will have a certain diameter. It is not possible, or it is rather difficult, I would say, that this would be a this would be an absolutely insignificant point, this point I am talking about. Okay, so it will have some diameter, even that diameter might be in the order of micrometer, right? So that is also a necessary factor for us. If I'm talking about that, this is the beam crossover, the diameter of this beam crossover is d naught, right? So this d naught will be in the order of, let's say, micrometer. But we know that if even if it is in the order of micrometer, if we want to characterize any structural features in the image, then we need to get the minimum d naught as possible. Okay, so what do we do? Let's say our specimen is situated somewhere here, so we with the help of other set of lenses, or other set of deflector, or so this is what I'm calling it as condenser lens, and let's say there is another lens called objective lens, right? So with the help of other sort of lenses, and in between the apertures are also there. So with the help of entire system, what we try to do, even from micrometer, we try to put the incident beam to as minimum as possible, and here it is in the order of micrometer. This is called as this beam, with the beam which is fallen onto the specimen, this beam is called a, so this the electron which carries the current which carries the electron of the beam which falls onto the subject, that is called as probe current, right? So now this is, I am calling it as the crossover, beam crossover, and here I am calling it as the probe. Okay, so from micrometer I want my probe dimension to be in the order of nanometer. So this is what from micron. So generally in an optic axis, we generally in a microscope, the job of a microscope is to magnify. That means if it is a very small size, then its job is to make it a big size. But here what I am doing, from beam crossover, right, from here in the order of micrometer, I am converting this micrometer with the help of other aperture, other lenses, lens system, in the order of nanometer. That means I am from micro to nano, I am reducing this beam size or the beam diameter. So that is what the meaning of demagnification. And remember that this demagnification happens in the order of 1000. If I am talking about, this is a tungsten, okay, if I am talking in terms of tungsten, which is a thermionic source, so 5000x, the demagnification happens in the order of 5000x. That means if I let's say if I take an example, like for generally for tungsten, it is in the order of d0 will be in the order of 50 micrometer, but we know that the probe size, when it comes and falls onto the sample here, then it will be in the order of 10 nanometer. Okay, so this is what I mean the demagnification. Similarly also here it is in the order of 5000, but for a FEG, that means a field emission gun, we know that the here the d0 for a field emission gun is already very low. That means it is in the order of, let's say, 10 nanometer. Already this d0 for an FEG is in the order of 10 nanometer. Still, even if it is in the order of 10 nanometer, we can make the probe tip here like this much. Let's say I am calling it as DP. We can put this probe tip in the order of 1 nanometer. So this is what the physical significance of a demagnification, right? And last class also we went through another concept, that is electrostatic lenses and electromagnetic lenses, and suddenly we saw that why we switched from electrostatic to electromagnetic lens. One of the main reason that we switched from electrostatic to electromagnetic is because electromagnetic lenses had smaller aberrations, and always we want as minimum aberration as possible, so that our image would look sharp and it would remain in focus for a longer period of time. Then comes another thing which is related to the it is a basic characteristics of an electromagnetic lens. If I say, then that is called focal length, right? So what is this focal length? We know for an optic for a glass thing, we can see, let's say this is a glass lens and this is an axis, so this is an object, and then so when let's say this is this is the f, and we know that this is the focus. Okay, this is the focal length for a glass lens, because for glass lens we have seen the focal length. We have also we have carried out some physical experiments also earlier. We might have carried out physical experiments at certain point of time in our life, so we know how the glass lens acts. But how the electromagnetic lens, when I say the focal length of an electromagnetic lens, what does that mean? The focal length in an electromagnetic lens means the distance from which the electron starts spiraling to the distance it crosses to the optic axis. That means, let's say this is the lens and electron is coming, so let's say from here it starts spiraling. Okay, it starts spiraling and coming down to this thing, and the moment, if I am talking, this one is my optic axis. The moment it starts spiraling, right? The moment it starts spiraling to this optic axis, to the first crossover at the optic axis. If I am talking about, this is the crossover of an electron beam, and these are the lengths. So this is what I call it as the focal length. Okay, and these focal lengths are actually they depict that how much electron can based on this focal length we can depict that how much accelerating potential we might need for our electron beam to put onto the specimen, and how much current we need, and that formula that is given by this formula, F is equal to V naught Ni square. So here F is the focal length, okay, and V naught is the accelerating potential. Or we can say it beam accelerating voltage. Instead of saying potential, beam accelerating voltage. Here not potential, it will be rather correct to say beam accelerating voltage, because here it is an anode would be there, and anode's job is to make this electron beam accelerate so that it would go down towards the specimen, right? And beam accelerating voltage, N is the, we know that N is the number of turns in the pole piece of the this lenses, and I is the amount of current. Okay, so here we can see that F will be given by V naught divided by Ni square. So here we can see that to keep, let's say we don't want to disturb, we have made an SEM and we don't want to disturb the focal length of our electromagnetic lens, then what we can do, if we want to, we don't want to disturb this F value, we want to make it as it is, but there will be samples which will be coming, which require a little bit higher accelerating voltage to see the features, and there will be samples which need lower accelerating voltage to see their features. So that means my V naught here I am writing on top right. That means if I want to keep F same, then, and in case my V naught is increasing, then what do I have to do? I have to also increase the current, right? So that means if to keep the same focal length, the SEMs earlier days we have to manually do it, but now in modern all the modern SEMs, so they have that system that they automatically compensate for these two. Let's say I am changing my voltage, my beam accelerating voltage, then automatically current in the coil starts to increase, right? So this is what I mean the electron focusing. Okay, and the demagnification, the formula for the demagnification, if I want to write it somewhere, so we know that here in the top left I'm writing, I hope it is visible to you. So we know that the thin lens equation is 1 by F is equal to 1 by P plus 1 by Q. Here P is the object distance and Q is the image distance from the length. So the magnification, let's say I am talking in terms of capital M, the magnification is given by small q by P. That means my image distance divided by object distance. But the demagnification, if I am talking in terms of small m, that will be given by my object distance divided by image distance. So this is the term, you have to remember it here, right? So now coming to imaging modes and operation. So this is an important section of SEM, because we want to see how we have produced our beam. Now we want to see how the beam is coming, but if we want to put any aperture, if we want to vary our specimen distance from the lenses, and if we want to vary the condenser lens strength, right? Based on these features which I have written it here, how the imaging modes will be affected, and what are the resolution, let's say resolution, or what are the magnification, what are the beam current that is flowing to my samples, all these things we have to look for. And why we have to, why do we have to look for? Because we want IP. There are three terms, one is IP, another one is DP, another one is alpha P. So remember, P means so subscript P here means I am referring to the probe. That means now I am talking when my sample hits, when my incident beam hits the electron, hits the sample, At that point I am talking, at that point I want dp to be as small as possible, at that point I want ip to be as large as possible. But we will see in subsequent slides that these two are contradictory to each other. Okay, how they are contradictory we'll see. And also we want in certain cases alpha p to be an optimum value, not necessarily to be high, not necessarily to be low. Why? Because last class we have seen that due to the aberration. We'll also go through the same aberrations today also in detail. So we want to optimize these three, because these three ultimately will decide how I will image my surfaces, how I will image my samples. Okay, so this is the reason that I want to see the effect of working distance, the effect of this aperture size, and the effect of condenser length strength. So if I am talking, let's say I have talked about P and Q, that means object distance and image distance. Let's say I am talking, so here I have taken one thing, this is, let's say I am taking as D0, right, and this is where my sample is. Okay, and here I have put objective lenses. These are the objective lenses, and this is actually the aperture inside which my objective lens is there. Okay, and let's say here is my condenser lens. Okay, so this is my condenser lens. Here this is objective lens as well as objective aperture. Okay, so this is how I have designed my SEM. And this is D0. So what did I tell you about the D0? D0 is the first beam crossover from the beams which are coming from the electron gun. So let's say I have drawn it a little bit larger, but for now you assume that this is in the order of micron. Okay, so now all the this is the optic axis, and this will be imaged like this. So now what will happen? The they all will come here, right, and then like this they will go, right, and here they will create another, and this will not be a point. Why I am not taking it as a point? Because the condenser lens, the beams which are coming in this direction, they will be focused to at a point, and the condenser lens will focus try to focus them at a point, but still there will be some kind of spot will be created. Why? Because this lens has aberrations. We cannot completely remove all the aberrations, so this will also be focused, this will also be having some diameter. Let's say this diameter is D1. Then you can see the, and if I am even taking some lenses, they all will be coming like this. Okay, so here let's say now for this objective lens, this is objective lens, so this D1 will now act as an object. For this one, for condenser lens, this D1 is the image. For objective lens, this one will act as the object. So now from this object, let's say this is this object, again the rays are coming. Some rays will be going in this direction also, but all the rays will not pass through this objective lens and aperture system. Why? Because this the job of this aperture is to block unwanted rays. So what it will do, it will only pass the rays which are coming, which it will only allow to pass the rays which are coming in this directions, right, to the extreme end. Other rays in this region which rays are coming, they will be completely blocked. So now what it will do, it will try to focus it here. Based on their inclination angle, it will try to focus like this. Okay, so that means so for now we will define some of the terms first. Let's say one of the terms I am defining. So here from lens to the first from beam crossover to the next crossover. So this will be the, since this condenser lens, this one is focusing all the rays to in this point, right, in this point the condenser lens is focusing. So that means this one will be known as the focal length of this condenser condenser lens. Let's mark it as f1, right, and since the D0 is this one, and this D0 is the beam crossover is from the electron gun, it is acting as a as an object for this condenser lens, that means this one will be denoted as the distance from distance of the object. This is p1, right? But then what will happen? Here the image will be formed, right? The image will be formed, but it is not necessary that all the rays will be accumulated accumulated on the plane of f1. Why? Because there will be some rays accumulated towards the top, toward above f1, and there will be some rays who will be focused, not accumulated. There will be some rays who will be focused above this focal plane, and there will be some rays who will be focused below the focal plane. That means we have to select now the disk of least confusion. Let's say for now the disk of least confusion is not equal to f1, right? So that means this distance for which so this is the disk of least confusion. So this distance I am talking it as q1. Okay, now if I am talking, so from q1, let's say the image is formed in the q1 plane, let's say in this plane. So this image which has been formed by the condenser lens will now act as an object for this objective lens. Okay, so then from there, that portion I will have the next object distance of the object. And again similarly, what will happen? This is my sample. Okay, since this is my sample, again this distance will be q2. I want my sample to be in the plane of the top surface of this sample, in the plane of disk of least confusion. However, the focal length might be vary for the objective lens, and that will be given as f2. This is a very cluttered drawing. I hope you are following me. To make the long story short, so this will be our first object. Okay, so this will be our first object, and this will be here, this will be our first image, and this image will again act as an object, and here it will be the image plane. And image plane means I am talking about Gaussian plane, which is given to the disk of least confusion. Okay, so and p1 p2 are the object distance from any lens, let's say condenser lens or objective lens, and q1 q2 are the image distance from any lens, and f1 f2 are the focal length for. So there are 6 terminology I am writing: p1 p2, then q1 and q2, and then f1 and f2, right? So these are the 6 terminology that we have to check. So based on this figure only, we have to decide what will happen if we change the working distance, what will happen if we change the aperture size, because we have inserted an aperture here, we have kept our sample here. Okay, so similarly, if we want to change the focal length, if we want to increase the current in the condenser, then it will, or we want to make the condenser lens as strong, then what will happen? We will see those things. So the effect of aperture size, if we want to see the effect of
Sorry, just can you just, I got network got disconnected. Just can you repeat some last 2-3 minutes? I could not concentrate.
Okay, so basically this is the beam crossover d naught, which we are taking it as the first object for this condenser lens here, right? And the distance is given by p1. Okay, and then this condenser lens will have its own focal length, which is given as f1, and based on its focal length it will form image on a disk of on a plane where we will get disk of least confusion. So that distance, the image distance from the lens, condenser lens, is given by q1. Same terminology now we have used for objective lens. p2 is the distance of the object from the lens, q2 is the distance of the image from the lens, f2 is the focal length of the objective lens. And how the image will be formed? Here the d naught will be, this one will be acting as the object for the condenser lens, and then it will form image somewhere in this plane. Now this image, or we can say it's an intermediate image. So this intermediate image will again act as an object for this objective lens, and then finally the image will be formed here, and where the image, the Gaussian image plane will be formed, or top surface of our sample will be there. So this is how a typical means we trace the electron rays in a scanning electron microscopy. Okay, so based on this varying this terminology, we are more focused now in this region. What will happen if I increase or decrease anything, so that my electron beam and specimen interaction, how they will take place, now we are focused in here. So that is why IP, DP and alpha P, these are the things we will vary. Okay, so effect of aperture size.
Sir, I have a small doubt.
Yes.
So this our desirable condition is D2 should match with Q2, right, sir? The
D.
second focus should be on the sample.
I
That is the
I
focus focal
cannot
point
hear
of the
you.
objective lens that should match with Q2, right?
Which one? F2 should be
Sir,
matching with
the
Q2.
second
You,
focus.
you are asking that one, right?
Correct. Yes, yes,
Yes,
yes,
yes,
yes.
yes. F2 should be
That should
ideally.
be the ideal case.
Yes, in ideal case, F2 should be matching with Q2. But since these lenses are having aberrations, so that is the reason F2 may or may not match with Q2. In ideal case scenario, F2 might match with Q2, right? Because
If you have not mark on the figure, I think.
yeah, F2 here I have put. This is the F2 and this is the Q2. So F2 is this one. This plane is the focal length. So this is the F2 plane and this is the Q2. In ideal condition, F2
But
and Q2 should match. Yes.
yeah, when F2 is matching with Q2, we will have the best resolution.
Yes, yes, we'll have the best resolution.
Okay, sir. Thank you.
Yeah, yeah. So we will see the effect of aperture size. Why we want to see the effect of aperture size? Because means until and unless we decide what is the optimum aperture angle, we will not be able to minimize the aberration on the final probe size. As I showed here, we want to reduce aberration on the final probe size, like in this region, let's say. So until and unless we decide how much opening we want, let's say this is my aperture now, and subsequently I am closing my aperture size. Whether I am increasing or whether I am decreasing, it depends on the kind of operations that I want to do. So here in case I am increasing my aperture size, decreasing my aperture size. Okay, down the figure. Okay, so what will happen when I decrease the aperture size? When I decrease the aperture size, one thing is for sure, that let's say more number of beams were coming initially. Now if I from 1, 2 and 3 condition, if I decrease my aperture size, then less amount of electron beam will fall on my sample, right? And since less number of electron beams are falling on my sample, then it will control control my image depth of focus. That is the idea of putting a large number of a big aperture and a small aperture, right? So that is how we have to select an aperture which will give you optimum angle, and because this aperture will only decide the final probe current, how much electron beam it is allowing to pass through. So this aperture will only decide. This aperture we generally put it in the object in the place of objective lens. Okay, and also this aperture will decide final convergence angle. What is the final convergence angle? Let's say this is my sample and I have kept my aperture like this. Then beams are coming here, a straight line. Okay, sorry. So beams are coming like here. Let's say beams are getting focused in this one, right? And then in this case, if I extend this thing, so this is my final convergence angle. Okay, and if I keep my aperture a little bit, let's say I'm keeping my aperture, so this aperture is currently, imagine, not there, so I'm keeping my aperture a little bit like this. Imagine this aperture in this place. Okay, then what will happen? These beams will be coming, and then so there will be the variation in the convergence angle. And why this convergence, why do we need to vary this convergence angle? We'll see it in the later slides when we are talking about the aberrations. That means we want like I told you, we want dp as minimum as possible, ip as maximum as possible, and alpha p is an optimum value. There is no thing called alpha minimum or something. So alpha p we want as an optimum value, right? So due to that, to get all these information, we have to check our optimum aperture size. Then comes to an effect of working distance. What will happen when to the electron probe or the incident electron beam? What will happen when we change the effect of working distance? So in this image, I hope you clearly, so whatever I have told, I have drawn earlier. So in this is the image that I was drawing earlier. So here you can see when we are increasing the working distance means the distance from the, so currently working distance means this q2. So q2 is the working distance in this figure. If I am doing that, if I am increasing q2, so this was my earlier q2 and now currently this is my current q2. So when I am increasing the and in this case what I am assuming that the aperture size should not change. If I am changing my aperture size, then in that case many variables will be there, aperture size as well as the other two like condenser lens strength. These two should not change. I am assuming this condition. Okay, under this condition what will happen? Everything else is remaining same. So here you can see this one. If I do that, then q2 is increasing, right? The moment q2 is increasing, I told you a term called demagnification, and the demagnification is object size by image size, or if we want to turn into the distance from the lens, then distance of the object from the lens divided by distance of the image of the lens. So in this case, if I am talking about m2, then it will be p2 by q2, right? Since q2 is increasing, right, if my q2 will increase, then my m2 will be decreasing, right? If my m2 is decreasing, in that case what will happen? My d2 here it was focusing, let's say on this, like this was my dp. Let's say I increase the distance, my sample is currently like that, then the ray which is coming like this, it is coming like this, it will have a much larger dp, right? And dp will be higher. That means I will get a larger spot size. If I am getting a larger spot size, that means what? My resolution will also decrease. Okay, my resolution will decrease, but in the case, let's say if my resolution will decrease, dp will increase means my resolution will decrease. However, other thing, let's say this is a flat specimen I have taken, or the flat specimen, normal flat specimen I have taken. If I want to consider the tilt specimen, let's say I am considering specimen like this. In this case I am talking about, in a specific case, let's say my probe size is falling in somewhere like this. This is my probe size, earlier probe size, right? So now if I at this point, so this is my working distance. So now let's say I decrease my working distance to somewhat like this. Then what will happen? Now it is covering a much larger probe size. So if I am covering a much larger probe size, that means I will be able to scan a little bit higher distance. So here, if from this scenario, if I am coming to this scenario, then the scan length will increase. And if my scan length is increasing, that means what? I am able to see, I am able to check this many the features which are available in this region. Scan length increases means my magnification will decrease. Okay, so these are the certain features that you have to keep in mind when you are talking about effect of working distance. All these things I do not want you to memorize. Rather, if you remember what is the conditions, this is the assumptions that we have taken, and what is happening. Working distance means q2, and then if you understand this figure in a correct way, then you will be able to solve the questions. And in ACM sections, in MCQs, generally effect of working distance and effect of condensation length strength are one of the most asked questions in the MCQs in ACM examination. Okay. Similar thing if we want to check for effect of condenser length strength. So condenser length strength means here you see now both image, my specimen are not changing. The working distance is not changing. Condenser length strength means here you can see earlier the F1 was like this much. Now the F1 is, you can see the F1 has decreased. Why? Because the strength increases. That means it will this lens will try to focus all the electrons beam as close to as possible, as close to as its axis to the lens axis, as close to as the lens axis it tries to focus. So that will decrease your F1. Since your F1 will decrease, right? If your F1 is decreasing, we know lens equation 1 by F1 is equal to 1 by U1 plus 1 by V1. In this case 1 by V1 plus 1 by Q1. If your F1 will decrease, similarly your Q1 will also decrease, right? If your Q1 is decreasing, then it will give to magnification. We will talk demagnification we are going to talk. P1 by Q1. Your Q1 is decreasing, P1 is as it is. That means your M1 will increase, right? Let's say now your D1 is somewhere here, right? This is your image plane for now after increasing the condenser length strength. Now from that image should act as an object for the objective lens, right? So now what will happen? This will be my P2. Since the Q2 value decreased, my P2 value will increase, right? Even if I keep my Q2 value constant, since my P2 value, that means the distance from objective lens, so this is my objective lens, distance from my objective lens to the intermediate image plane, which is called as my object distance for the objective lens, it increases, my M2 value will also increase. Even if this is remaining constant, P2 increasing, that means my M2 value is also increase. Okay, and since this thing M2 value is increasing, that like the demagnification is increasing. So earlier demagnification, if I was getting 50 micron, then demagnification, that means from 50 micron I would definitely go down. I'm just giving you a numerical example. It does not mean it will go to 5 micron, but definitely what will happen, this one, my final probe size, this will decrease. Why? Because my demagnification is increasing, right? So my final probe size will increase. So these are the three effects that we have to see. What are the optimum convergence angle? What is the effect of condenser lens strength on your probe size and probe diameter? What is the effect of working distance on the probe size and probe diameter, right? So now coming to a term called Gaussian probe diameter. So this Gaussian probe diameter is nothing but the probe size at the on the surface that we want to minimize. So why we want to minimize? So there are two terms, one is probe size, another one is probe current. So the probe size is given by dP, probe current is given by IP. We always want minimum probe size, okay, because as minimum probe as our will be able to resolve our resolution of the microscope will go high, and current will be high. Current should be high because we want many of our incident electron beam should interact with our specimen, then only we will be able to get much information from the specimen. So this is, but these two are contradictory to each other. So that is why and that's why considering that how to calculate what should be the ideal probe size, what should be the ideal probe size to calculate that one, first we need to consider an aberration free lens. Let's say I am considering an aberration free lens, then how we can calculate, we have told that earlier we know that brightness beta is equal to intensity like beam current density. Beta is beam current density per unit solid angle, right? So this was the formula. So beam current density, let's say I am considering, now I am saying beam current density, but that beam is currently I am talking about is a electron probe which is about to fall onto the specimen. So I will talk in terms of IP, right? Per beam current density will be pi divided by dp by 2 square, right? So this will be the flux beam current density, current, this is the current and this is the area, right? So this is the beam current density divided by unit solid angle. That means we are talking in terms of 3 dimension. Unit solid angle will be given by, let's say, convergence, the solid angle is now the convergence angle is alpha. I am talking in now that I am talking in terms of the probe current, electron probe, so I will be talking in terms of alpha p. So this will be my, so this convergence angle, if I rotate it in 3 dimensions, so that will give me my unit solid angle, right? So this term IP divided by pi dp square divided by 4 into pi alpha p square. So if I take this 4 to up, then I will be getting 4 IP divided by pi square dp square and alpha p square, right? This is what I will get from beta, that is the brightness of my final probe, right? Without any aberration. I am talking here that without any aberration, the brightness of my final probe. So from here, if I consider that this dp will be exactly on the Gaussian image plane. Gaussian image plane means the plane where the disk of least confusion is formed. That might be a point, that might be a disk kind of structure due to the aberration, right? So that is why I am talking about in terms of Gaussian probe. So if my dp will be in term, and now I am talking in terms of dg, that means I am talking the Gaussian, talking about the Gaussian probe diameter, then rearranging all these terms, I will get this expression. So you don't need to remember this expression, you just need to see the bright, you need to understand what is brightness. From brightness you can easily calculate this expression. So here we are seeing that even if you put a constant, if you want to let's say I am increasing alpha p in this expression, right? I am increasing alpha p, then what will happen? My if I want to maintain a constant dg, that means my diameter of the final probe I do not want to change. If I am increasing alpha p, then I have to increase ip, right? So these are some of the terminology that you have to check here, okay? And if my alpha p I am increasing, I don't want to change here. If I am increasing my alpha p, then what will be the limitation that I will have? The more you increase the convergence angle, the more aberration will come. Why more aberration will come? Because of the one aberration called spherical aberration. The more it goes away, the more your rays or your electron beam goes away from its optic axis, the more focused it will have, the more it will be focused, right? So that is what one spherical aberration is there. So if I have to keep constant Gaussian probe diameter, if I want to increase alpha p, that means my convergence angle, I have to increase ip. But in that case, what I have to do? I have to increase my aberration. So that means I randomly cannot manipulate all these things. IP or alpha p, I randomly cannot increase or decrease. So I have to limit the spot size. So this is the region that dg, we are not limiting. That means if you are increasing alpha p to an infinite value, this dg might come to a very finite value, even in the order of angstrom. That is this formula is telling us theoretically, but that is not possible because aberrations are increasing. And what are those aberrations? Spherical aberration, aperture diffraction, chromatic aberration. These are the 3 aberrations that we'll talk about mostly. Astigmatism we can easily remove from our electron microscopy by inserting stigmators, right? So stigmators are nothing but different kind of octopole which will based on their magnet, based on the electron beam, they will put the electron beam into the focal point, so that therefore means different rays will not vary. So astigmatism we can remove by applying stigmators. But what about the spherical aberration, aperture diffraction and chromatic aberration? Spherical aberration, chromatic aberration, we know spherical aberration means once the more it goes away from its optic axis, the more strongly it will focus, right? This is the concept of spherical aberrations. So this is what the concept of spherical aberration. This is the this is one focus, this is another focus, this is the plane of least confusion, right? And chromatic aberration, we know that the energy spread will be because all the electrons which are coming out of the electron gun, they will never have same energy, exactly same energy. Even that energy level is 0.3 electron volt, even if it is there, so some amount of aberration will be there. So for field emission gun, the this chromatic aberration is less, and the thermionic gun like tungsten and lab 6, the chromatic aberration is a little bit high. So chromatic aberration, we know. What is this aperture diffraction? Aperture diffraction means we are inserting some kind of aperture to limit our current. That means unwanted current we don't want which to fall on our sample. We only want this amount of current to fall on to our sample. But then this current, when they will come in contact of this any kind of any kind of edges or in their path, so here they will also start diffracting. They will not simply fall like this and for many minutes. Rather, what they will do, they will, let's say one current is coming, electrons are coming like this. This is my sample, and here so diffraction, here also they will start forming some kind of fringes. Okay, so this is what aperture diffraction means. And so these are the DS, DD, DC, are the three terms. What do you mean by DS? DS means the dimension of your the diameter of your probe due to the spherical aberrations, right? So spherical aberration will contribute to the diameter of the probe by this amount. So this is DS. Similarly, your diffraction, aperture diffraction will also contribute to your diameter of the final probe by this amount, and also chromatic aberration. However, this chromatic aberration is generally dominant below 10 kilovolt. Okay, so if you are talking about aberration, normal conventional SEM mode, so kilovolt, or if I am talking in terms of energy, then kilo electron volt, right? So this chromatic aberration is dominant in this region, but conventionally, if I am talking about, then 10 to 30 kilo electron volt is the operation range of SEM, if I am talking about a conventional SEM. So in that case, what I will do, I will consider, so these three aberration will impact my diameter of the final probe. If these three, and here one thing to note is that if I am increasing alpha, my spherical aberration is increasing in the order of 3, right? But however, if I am increasing alpha, my aperture diffraction is getting reduced. That means, okay, I have drawn it here. Okay, so I'll draw this figure here, try to draw. If I am talking about my final D, this diameter, and this is my aperture angle increasing, then for spherical aberration it will be like this, and for aperture diffraction it will be like this. So this is my DD, this is my DS. So that means I cannot randomly increase or decrease my convergence angle. So that to do that, what I will do, I have to put a minimum value. I have to choose an optimum value so that the aberration disk diameter will be least affected by the convergence angle. It will be affected, but least affected. So this is what I will call it as alpha optimum, this point. Okay, so I have to take an optimum value so that my spherical aberration is not high, my aperture diffraction is also not high. So considering all the four, my minimum probe size I am counting. So remember, earlier my DP, when DP was equal to DG, I simply had one expression, but now I have to add all these things. So the final probe size will be dg squared plus ds squared plus dd squared plus dc squared to the power 1 by 2, right? And minimum probe size, if I am talking in terms of 10 to 30 kilo electron volt. Okay, so this is the potential I am talking about. If I am talking in terms of energy, then I have to add electron volt, right? So then spherical and diffraction effect are taking place, and neglecting chromatic aberration, I will have this term. The D minimum value, if I am talking about, I will be getting this term. Here CS is the coefficient of spherical aberration, IP is the probe current, beta is the brightness, lambda is the wavelength. Here lambda is also the wavelength, right? So here one thing to notice that as we are increasing brightness in this expression I am talking about, as we are increasing the brightness, that means my D is decreasing. And what do I want always? I want my brightness to be high and my D is also to be as low as possible. So this is the practical size of practical limit for a minimum probe diameter. However, we have to consider sometimes the theoretical limit. Theoretical limit means if what is the microscope's theoretical resolution considering the spherical aberration, that you do not consider the diffraction and you do not consider any other aberration. So what is the in that case what will be the minimum diameter? So that will be somewhat this much. D minimum will be equal to similar to lambda to the power 3 by 4 and Cs to the power 1 by 4. This is an important expression. And if you want to, let's say if I want to remove this proportionality sign or anything, then I can put lambda is equal to always 3 by 4 into Cs is equal to 1 by 4. Okay, so Cs here is the coefficient of spherical aberration, lambda is the wavelength. So if when let's say when someone talks that if my lambda is decreased or increased by this much, then what will be, how my probe diameter will be affected. That means he is talking about the theoretical resolution, that what is the final theoretical resolution that you will get. If my coefficient of spherical aberration increase or decrease by this much, then what will happen in that case. Okay, so this is an important expression you have to remember. And similarly, if we are considering all the aberrations, in that case you can manipulate the previous rearranging the previous terminology, then you will get Imax, because our initially, so probe diameter should be as low and probe current should be as high. So Imax D min, the diameter should be minimum, current should be maximum. So you will get this terminology. Okay, and so these are, and yeah, so I think yes. And if you want to see the performances in the ACM, like there are different kinds of performance. You cannot go to a single set of parameters saying that I will get everything. So you have to decide which part you want to focus your beam on, and then accordingly you have to decide. We generally map our material or specimen. So there are different kinds of modes are there. One is resolution mode, high current mode, depth of focus mode, and low voltage mode. So these are the modes for just for your information. I have noted it down here. One thing is depth of focus mode. So depth of focus mode is here this mode we will get when we are inserting a small aperture. Small aperture means we are blocking many of the current. So when we are blocking many of the current, let's say current is coming and then we are blocking, this is our specimen. So in this case we are getting depth of focus mode. We will see how the depth of focus mode works later, but in small aperture means small convergence angle also, if we are keeping our working distance same. Okay, in in that case large small working, if we are keeping our working distance same, then in that case small convergence angle. And depth of focus, if we are increasing that large working distance, when we are increasing the working distance towards here, then in that case also our convergence angle will be low. In that case we will get more depth of focus, so that we will be able to map different features which are situated different at a different height from the objective aperture. We will see that in the subsequent slide. So these are some kind of modes that ACM operator generally operates. So now coming to now we have decided what will be our DP, what will be our D min, what will be our Imax. Now we want to see that after interacting with the specimen, what will happen. Ideally, why we should why we should think that electron beam specimen interaction is important, because we just before we have told that our D min, like let's say I am talking about D magnification 1 to 2 nanometer for an FEG gun, right? So if we are talking about in the order of 1 to 2 nanometer, then why do we have to talk about this there is a term called interaction volume when electron beam is incident on specimen. Why do we have to see in that case? Because 1 to 2 nanometer is sufficient, and my features are not more than in the order of nanometer, because my features are also in the order of micrometer. And if my probe size is nanometer, then I should ideally be able to map those features. But then what is happening? The problem is my electron beam, when it is going, it is starting to deviate all because of its interaction with this sample. Let's say this is my sample, and from here my electron beam is coming. Then it is interacting with, first of all, it will penetrate with the to the sample. Then there are two phenomena that will take place. One is elastic scattering, another one will be inelastic scattering. Why this thing? Why I have to consider this elastic scattering and non-elastic scattering? Because the electron, when it enters from 1 to 2 nanometer, let's say I want to calculate, I want to see this is my specimen and my probe is coming in this region, right? Then I should be able to get information from this one, and then my job is done. But instead of that, how the interaction affects our information, that the linearly, if you see my beam is coming in this region, if you talk in this region, the linearly, the range of information that I will get, that will be the range from which I will get all the information, compared to this 1 or 2 nanometer, that range will be 1000 times more, right? So ideally I should be able to get information from 1 or 2 nanometer in this range, right? But the range from which I will get the information, if I am talking in terms of linearity, then it will be 1000 times. And if I am talking in terms of 3 dimension, then it will be nearly a billion times. That means the information I will get from the sample, let's say this is my sample, the information that all those information are coming from an area or from a space which is much larger. That means 10 to the power 9 order of 10 larger. I will get the information. So that is why I need to know, I need to verify which information is coming out of the specimen. So that is why we have to study the electron beam and specimen interaction, right? And so the elastic scattering means, so in the elastic scattering, what will happen? The electron beam, so this is my electron beam. If I am talking in terms of three scenario I am taking here. So this is my incident electron beam. When it is, and I know my specimen is having incident electron beam is negatively charged, right? So when I am talking, a negatively charged particle is coming and interacting with my specimen, then what will happen? My specimen is having infinite number of atoms, and all those atoms will be having infinite number of nucleus, and nucleus is positively charged. Since this negatively charged electron beam are coming and it is interacting with positively charged nucleus, that means some amount of attraction will be happening, and due to that attraction the electron beam changes its path, and due to that I will get different kind of scattering. Okay, and based on this attraction, or in some cases repulsion also happens, because incident electron beam and the outer shell electrons are also sometimes they also repel, because both are negatively charged, though the amount of repulsion is almost insignificant to the force of attraction, but that case will also happen. And elastic scattering is the scattering where the incident electron beam, let's say, coming, and here is my positively, so this is my negative. Here what will happen? They will only deviate from their original path, but no energy loss. That is what called as elastic scattering. Here one atom, positive atom is there, they have gone to this position. Now let's say in this position another positive atom is there. So what will happen? Again they will start to deviate. Here another positive atom is there, again they will start to deviate. That deviation might be any deviation between 0 to 180 degree. We should not think that they will not go back also. If a strong positive nucleus is attracting them, then they will also start to deviate. So that deviation angle will be 0 to 180. So due to in this kind of motion, when, and this is what is happening here, I have shown it in 3 dimensions. Okay, and here this is, they have changed their path one time, here multiple 3 dimensions when I am talking about. So here they have changed their path many times, but they might change their path. The incident electron beam I am talking about, they might change their path, but they should not lose any energy, and that is what called as elastic scattering. And this elastic scattering increases with atomic number Z. Okay, the heavier, why it increases, the reason is the heavier the atom, much stronger positive charge is there, so it is able to deflect them from their original path. And this there is a term called, there is a term called the probability of there is a term called Q, which is defined as the cross section for elastic scattering. Okay, so it is a very complicated expression. You just need to remember this Q will be directly proportional to G square by E square. This is the term you have to remember. Q will be directly proportional to G square by Q square. And so here the probability of elastic scattering increases with atomic number G. And how does it increase? It increases proportionally by square. And E, what does this E means? E means this is the energy of the incident electron beam. So this E, okay, so this E means energy of the incident electron beam, right? So if you increase the atomic number of an element of your sample, let's say you are trying to see any an heavy element, then in that case the elastic scattering will increase. If you keep the constant let's say energy for your incident electron beam, in that case the cross section area for the elastic scattering will decrease. Okay, so this is the terminology that you have to remember. So Q is there are lots of constants are there, and it is also a trigonometric function. So the most important thing you should remember is that it is proportional to Z square by E square, inversely proportional to incident electron beam energy and directly proportional to the atomic number. So this is what elastic scattering means. But instead of elastic scattering, let's say elastic scattering will not always happen. Why? Because if it is if they are the electron beam with high kinetic energy, they are coming and impinging on our material. In our material, atoms are there, and atoms are made of nucleus, that means proton, neutron and electron. In nucleus positive charge is there, but we should not forget that around nucleus negative charge electrons are also there. They might be loosely bounded, some might be tightly bounded, but still they are there. So what will happen when this high energetic electron beam are coming and hitting them? There will be some amount of transfer of energy will take place. Those transfer of energy, the moment the energy starts to transfer from incident electron beam to these electrons which are staying in the atom, then that is what called as inelastic scattering. And in this inelastic scattering, the direction might also changed. Okay, so this is, and this energy change happens does not happen simultaneously. It happens gradually, slowly. That means if my incident electron beam is E naught, then from 0 to E naught, it is a gradual change. It should not, it does not take place in an instantaneous manner. Okay, and so how to calculate the elastic scattering? So Hans Bethe, if you he's a well-known scientist, so he has given one range that is called as Bethe range. So that what does that Bethe range tells us? So this tells us this: an estimate of total distance an electron travels in the specimen. And you should remember this total distance should be along the trajectory. Along the trajectory means, let's say my specimen is there like this, and my sample is coming here. Anywhere I can go, but my Bethe range will be along the trajectory. Though the distance it has traveled like this, anywhere like this, but the final Bethe range which I will talk about, that is in this section. And this Bethe range will tell us how much elastic scattering is happening. Okay, and like I said, E naught will it's the energy change, or the energy, more importantly the energy loss, which will be happening over a gradual period of time. So you can see for gold, for copper, for silver, for copper, aluminum and carbon. So you can see the incident beam energy, how energy loss, how they are happening. Okay, and the Bethe range is also, you can see Bethe range is changing. and this Bethe, this energy loss is also given by this Hans Bethe, how the energy loss is happening. That means it is happening gradually. So he has given a term. So that there is also another complicated term is there. So you should means I'll just write some of the proportionality A E I ln 1.6166. Okay, there is another constant is also there. So here Z means the atomic number, rho means the density of the material, A means atomic weight, EI means energy of the incident beam. Okay, so these are some of the terms you have to remember. So this is the most importantly Z and EI. These are the terms that you have to remember how in elastic scattering the energy changes happens over a period of time. Okay, yeah, this is the Bethe range, and now we will see that we know that interaction when incident electron beam interacts with our sample, and interaction volume, this interaction volume is generated. But what does that interaction volume has to do with the influence of beam energy? What does that interaction volume, or how does that interaction volume change when we are changing the tilt angle? All those things we will see it. So the beam energy, that means here this is the beam is coming. Okay, so this is, let's say this is 30, this is 20 kV, this is 10 kV, this is 5. Though the images are were small, but you can enlarge it, and then you can see means you can put them in a proportional size, and then you can see. So here what we are seeing, this is a copper specimen that we have taken for all the copper specimen. So here you can see so this is 30 kilo electron volt. As you increase the incident beam energy, that means beam energy, if it is increasing, the interaction volume will also start on increasing. Okay, so interaction volume increases as we are increasing the beam energy, right? And this kind of image you can do with a software named, I think, Casino, the name of the software. This is the software which will allow you, it's a simple software, you can also download it and see for yourself, and that how this is the Monte Carlo simulation software, that how the electrons, you can give electrons a certain amount of energy, and then you will see how according to the beam energy the interaction volume changes, right? And then we'll talk about atomic numbers. So okay, I don't know why there are no names are written. So this is carbon, silicon, no, this is copper, this is Ag, this is Au. So these are the different influence of different interaction volume based on their atomic number. As you can see, when you are increasing the atomic number, right? So when you are atomic number, that means the Z is increasing, the interaction volume will be decreasing. Why the interaction volume will decrease? The interaction volume, I told you one expression, that is Q. Q is the cross section for the elastic scattering. Elastic scattering means the incident beam will change its direction. So Q is directly proportional to G square. Since G will be increasing, so the elastic scattering, the cross section will also increase. That means the beam which is coming in this direction, it will get more and more cross section to scatter, right? So this is what the cross section means. That means it will scatter in more different, instead of going straight, it will try to scatter. So this is what the scattering cross section means. Since this will be is directly proportional to Z square, so that is why it will scatter more. And if it is scattering more, then it will try to stay as close to the surface as possible, not coming deep into the surface. So this is the reason why when you increase the atomic number, the interaction volume in linear dimension, if I am talking this one, I have to be clear, in linear dimension, right? In linear dimension it is decreasing. And another thing, when I am talking about specimen tilt, either I can tilt the specimen or I can tilt the beam. So when I am talking about the tilting of the incident electron beam, then you can see this is a 0 when I am my incident electron beam is hitting the specimen at a normal to its surface, right? And when it starts increasing, that means this tilt is increasing. Currently it is 0 degrees. So remember, the tilt is always count from this side. Okay, this is the normal for a if you are talking in terms of interaction volume, then tilt will be always considered from this one. So this one will be considered as 0 tilt, this one will be considered as 45-degree tilt. Okay, so similarly, so when you increase the tilt, what will happen? The interaction, the electron beams are coming. However, here they are going to a much deeper depth. But let's say the high energetic electron beams are coming at 60 degree of specimen tilt, then there is chance that here there are, let's say, many atoms are there which are positively biased, or nucleus are there which are positively charged. So here there is much more chance that immediately they will try to go out of the specimen. If they are trying to go out of the specimen due to elastic scattering, then the penetration depth in the linear dimension will be small. So if I increase the specimen tilt, then what will happen in that case? Penetration depth will decrease. Okay, all of this I am talking in linear dimension. That means linear dimension means the trajectory of the incident electron beam. Okay, so this is what will happen regarding the interaction volume. Then now we have our specimen has interacted with the incident electron beam. Now we will see what will happen after the interaction, after the signals which are coming out of the interaction volume. So there are there are two primary signals which will be coming out of our specimen, and so those are called as BSE and SE. We have seen those things. We'll just go through them once again. So BSE is backscattered electron, SE is secondary electron. So these are our primary signals which are coming, and also there is another secondary signal is also coming. Those are X-ray. So primary signal, this SE and BSE, we use them to see many microstructural features, and X-ray we generally use it for EDS, energy dispersive spectroscopy, which is where we try to see the compositional details. Okay, like how at which place the materials are, any particular element is there, right? And so here the energy distribution curve, if I am talking about, so all the signals which are coming, you can see here, this is E by E naught. So this is the E by E naught. So BSE, the backscattered electron, right? That means the energy of the electron, which are now I am not talking in terms of the incident electron beam. Now I am talking in terms of the signals which are coming, or the electrons which are coming from the specimen, right? So two types of, I will be focusing my study on two types of signals. One is BSE, another one is SE. So here backscattered electrons are the electrons which are deflected many times, or which are scattered many times by the atoms or by the nucleus in the sample, and then they start to come out. And this BSE, that means backscattered electron, they are heavily their energy is high. So there are three regions, you can see 1, 2 and 3. So in the one region, in this region, there are generally BSE are there, backscattered electron. There backscattered electrons energy range is generally stays in this region. Here this range is called as transition range. Okay, here some backscattered might be there, some secondary electron might be there, and this third range, which I am zooming it to here, okay, so this is called as SE range. Okay, secondary electron, that means secondary electron, based on the energy that they have possessed, so secondary electron. And always remember BSE, that means backscattered electron, are the electrons which were coming with the incident electron beam. After losing energy in different way, they are coming out of the specimen. Those are called as a backscattered electron. Secondary electron are related to the specimen, or are they related to the sample that you are trying to map. Okay, so backscattered electrons are beam electrons. You have to remember this thing, whose trajectory have intercepted the surface. That means surface of this is specimen. Okay, so these are the backscattered electron, and due to multiple and numerous scattering, they have now lost a fraction of their energy, and now they are coming out of the specimen surface. It is not necessary that all of the backscattered electrons will come out from the specimen surface, and so some might come out. In fact, many come out, but there is chance that a fraction of the incident electron beam might be lost in the sample forever, right? And to see what is the amount of backscattered electrons that we are getting, so there is a term called backscatter coefficient, which is given by eta, which is the ratio of number of backscattered electrons that you are getting. So here, number of backscattered electrons you are getting. Now I am talking, this is my sample, I have put some kind of detector here. Okay, this is my incident electron beam. Now my detector is collecting all these backscattered electrons, right? And some ACS are also there, secondary electrons are also there. So number of backscattered electrons you are collecting by number of beam electrons, those are coming by here. Okay, since these number of backscattered electrons are charged particles, so we can also write this thing as current, because these are effectively negatively charged particles, electrons. So we can write that. So IBAC means this is the backscattered electron which are coming. So current corresponding to the backscattered electron which are coming from the specimen. This I beam is beam current injected into the specimen, right? These are the two terminology you have to remember. And how the atomic number dependence of BAC we will see. So atomic, this is the curve. I think someone in the previous class asked that why we are seeing the phase separation in by using BAC mode. So here we can see that the atomic, this is an experimental curve. So here the atomic number, as we increase, the backscatter coefficient are also increasing. And from our physics, from our interaction volume visualization also, we can see that if an element is having a heavier, let's say, if an element is having heavier nucleus, that means a strong positive charge, then there is a high chance that my negatively charged electron will be more likely to be deflected, right? Be it elastic scattering, be it inelastic scattering, there is a high chance. Let's say I have one small a light element, not small, a light element which is having a less number of positive charge, then my penetration depth of the incident electron beam will be more, right? So that means the number of backscattered electrons that I will get from a large atomic number will be much more higher than the number of backscattered electrons I'll be getting from a light element. Why? Because this number 2 element has less capability, or has small positive charge in its nucleus of the atom, that they will deflect. It is not I'm not saying that they will not deflect, but they will deflect, but not to the extent that these strong atoms are deflecting. So that is why the getting backscatter electrons from a higher atomic number is higher than from a lower atomic number, right? So that is why the atomic number, the contrast which will come from an element which is having higher atomic number is far larger than the contrast which will come from an element which is having lower atomic number. However, if you see here this curve, and now look at this one. So this is the backscatter. So this is the eta curve, right? Eta versus atomic number Z. So when you see, if you are looking at a number, let's say this is 50. So till 50 the curve, it's a steep increase, right? Till 50 the eta versus Z curve, it's a steep increase, but after 50 you can see the increase is not that much. Okay, so that means we can say one thing. Okay, so yeah, so here we can say one thing, that this atomic contrast is very high at low atomic number, right? If I am talking, let's say magnesium is 12 and aluminum is 13, right? So the contrast that I will get by backscattered electron between magnesium and aluminum might not be same, which will be let's say I don't remember the atomic element which will be having the atomic number of 99 and 100. So this is 12 and 13. So the contrast that I am getting in this case will be far larger than the contrast I am getting at this case. Okay, so you can see from this curve that this is how the backscatter coefficient or the backscatter yield will vary as atomic number, right? So similarly, the beam energy and tilt dependence of backscattered electron. Though here we are seeing that as we are increasing the atomic number, the beam the eta also increases, but unfortunately when we are increasing the voltage, so here you can see 10 kilo electron volt to 20, 30, 40, 49, right? So when you are increasing or even decreasing the beam voltage, the curve more or less remains same, because this shape is taking because of atomic number, right? Backscatter yield, whichever it is going because of the atomic number. But for all this cluttering, if you can see, even if we are increasing or decreasing our atom beam energy, so these are the variation in the energy, my backscattering coefficient is not varying. Why it is not varying? Because the moment you are applying more energy, it will also, inelastic scattering will also take place simultaneously. So the moment inelastic scattering takes place, then we are talking about Bethe's equation. The loss at which the energy will also happen will also be increased. The penetration depth, if you are saying that your penetration depth will increase, then the loss at which the incident electron will lose its energy will also increase, right? Since these things are these things will give you that the beam energy will not have much significant effect on the backscattering electron yield, right? So there is another thing also, beam energy will not have significant effect, but tilt dependence. That means if you are talking in terms of tilt, let's say these are the different materials I have taken. So this is my backscatter coefficient, and this tilt means at which angle I'm like earlier I told 0 degree, 45 degree, 60 degree. So if I am talking about in terms of tilt, then when my tilt angle increases, my backscattering coefficient is also increasing. That also means we can also see from here that tilt increases means my atom, let's say there are lots of atoms are here. In this case, just consider I have told you. So my tilt angle increases means there is less chance that my atoms my electrons will go under go to much penetration depth. In that case, what will happen? If it will have a less number of elastic scattering or even inelastic scattering and then go out of the specimen. Once it goes out of the specimen, I will have my detector here, and then I will get the backscattered electron, right? So it is the dependence of backscattered yield based on the tilt is monotonous. It increases monotonously, okay? And this image is actually, this is for a single element and these are for different element. Now come to secondary electron. We know that secondary electrons are the electron which are having energy of less than 50 electron volt, okay? And due to their low energy, they are easy to collect. Backscatter electrons energy, if I am talking BSE, then they will be 0.7 to 0.9 of incident electron beam, which is very high. But here if you are talking about, in terms of electron volt, right? And similarly to eta, there is also another term called delta. So this delta is NAC by NB, that means beam, number of electrons into beam, and then here NAC means number of electrons which are coming, number of secondary electrons which are coming from the, so here remember this is the specimen I am talking about. Secondary electron means I am always talking the electrons which are coming out of the specimen, right? And how does the secondary electron vary with the depth? So the secondary electron, as we can see, just Yeah, so as the secondary here the more depth you go from the interaction volume, there is the yield will be very less. Why? Because there is less chance that, let's say this is my material, from here my material starts. Okay, let's say from here my material starts, and an electron which will get energy from here, let's say excitation energy it got, but it has to cross all the way through this, right? So as depths as you go, the chance of the getting the secondary electrons is very very low. So similarly, there is another concept is also there, which is called as, this one is called as shallow escape depth. Okay, so what does means shallow escape depth means, so generally they will first enter, right? Let's say one electron has gone through multiple of scattering, then finally it has got energy from here, and then it is not necessary that immediately it will go out, so it will also goes through a certain number of scattering, and then let's say after while going, so this is my incident beam, and this is my BAC. Because why I am talking of BAC, because these beams are coming out of the specimen after interacting with the specimen. So what will happen here? So and this depth is given by 5 lambda. This shallow escape depth is given by 5 lambda. Here the lambda is not the wavelength, this is the called the mean free path, and the mean free path is the path between two scattering, I think I have written, no. So the mean free path is the path between two scattering events. Like one electron has got energy, does not necessarily it will go out of the specimen, it might scatter into another electron. So the scattering, so due to that the scattering also take place inside the interaction volume. So that is this shallow escape depth. That means if an electron is inside this 5 lambda, right? 5 lambda means this lambda is the mean free path. If the electron is inside this 5 lambda, then there is a high chance that electron of the specimen, not electron which was coming with the incident beam, electron will go out of the specimen, right? And then when we come to the image formation, that means we have dealt with the backscattered electron, we have dealt with the secondary electron. Now when we are talking about image formation, then the image, how will we see how the image formation happens? Let's say this is my incident electron beam, and this solid line, so there are different kind of 1, 2, 3, all these up to 9 it has been there. So each point, let's say each point it will start scanning, like in this manner it will start scanning. So that is why, since it's a, this is the top image, if I want to, the top view of this specimen, if I want to show, then let's say this will scan like from A to B, then from B it will again, let's say it will come to C, this is the point C and this is the point D, then again it will do the scan. So like this beam, okay, this is the beam, these all are just the schematic representation of how the beam moves. So this beam will scan like this, then again it will come back, again scan like this. It will not scan from B to C, okay, it will not scan like this. So that is why the name is scanning electron microscopy. And there another term is there which is known as the magnification. And this how do we see through the let's say scanning happens, then how do we know that this scanning is happening? Then this is our specimen, and then there is a whole set of system is there, like detection system is there, detectors are there, and not only detectors are there, but detector with amplifier, photomultiplier and linear guide, all those things will be there. And So based on the entire detector system, and finally we are able to converge whatever it is the electron beam has scanned on this specimen, it will be displayed on the CRT, cathode ray tube. Okay, so CRT it will be shown, and here the magnification will be given by L by L. So L here is the length, I can say length on CRT divided by so here small l is length on specimen, that is the magnification on a microscope. Okay, so this is the magnification of a microscope that we are getting. So the length of the scan on the cathode ray tube, that means here, divided by the length of the scan on the specimen, that is how we are checking our magnifications. Okay, here this is a typical SEM image in the left side. Here you can see the various features, and with the SEM image there are various features you should able to see. So this 10 micrometer is the scale bar. Okay, and so here you can see AC means it has been taken in secondary electron mode. Mag 1000x, that means this is the magnification which is having 1000x. HV 20 kV, that means the energy of the incident beam, it is 20, the potential, and the energy is 20 kilo electron volt. WD means 11 meter, means this is referring to the working distance. So working distance is the distance between your specimen from the final aperture. Okay, so these are the different typical information that you get with an SEM image. And with the magnification there is another term also you should remember, which is called as pixel. Pixel is nothing but size of the area on the specimen from which information is collected. If we go here, so pixel is the, let's say this, consider this one. So from this dot currently the area the information is collected, right? So that is what called the pixel, and that information is transferred to the CRT, cathode ray tube. Okay, so there is another concept which is associated with depth of field. So the depth of field is we will see here how that depth of field, because this is also sometimes they ask these questions based on the concept as well as the numerical also they ask. So here depth of field means, let's say my specimen is this one, my specimen, and I want to see what is happening. Let's say if this is my focus point, perfect focus region, but I want to see what is happening from here to here. It is like simultaneously. Okay, so if I am considering this is my D, okay, depth of focus, or in SEM also sometimes depth of focus or field, they are interchangeable in case of SEM only. Okay, not in case of TEM or in case of optical microscopy. So sometimes you will see in many textbook depth of field they have written, also simultaneously they might have written in bracket depth of focus. Okay, in only this happens in case of SEM. So this is the plane of optimum focus, right? But I want to see my image, whether I can image from here to here, right? So if I want to do that, then my depth of field should be very high, then only I will be able to see. That means this, from this portion to this portion, my object should be in focus, and similarly my image should be in focus. There should not be any disturbances. Let's say why I am saying I have taken an inclined plane, because let's say I am going to image one fractured surface. My fractured surface is like somewhat like this, right? So in this case what I will do, if I have large depth of focus, then I will be able to get information from this point. I will also be able to get information from this point, right? So that is why my depth of field I want to check. That is what is my depth of field based on my spot size, or based on my convergence angle, right? So here if I am talking in that this is the depth of field, so this is D I am taking, that means this will be D by 2, and this is the alpha. This is alpha, means this is also alpha, right? And if this is alpha, then my minimum beam radius, like if I am considering my minimum beam radius, or the beam radius, beam size, the spot size will be given by dp, right? But here I am instead of diameter, if I am choosing this one, right, this one is the radius, then I can write here according to this. Now I am just putting the triangle here. In this triangle I can write tan alpha is equal to, this is r divided by d by 2, right? So I can write this one, tan alpha is equal to r divided by d by 2. Since this alpha will be very very small, so I can write it here, tan alpha will be alpha, right? So in this case alpha will be 2r divided by d. Okay, if I want to measure for my d, then d will be 2r divided by alpha. So this will be my ultimate expression for depth of focus. If I want to increase my depth of focus, right, if I want to increase my depth of focus, then my alpha should be as minimum as possible. As minimum as possible. So that is the reason I was saying in the earlier slide that if you are and how this alpha will be as minimum as possible when you are decreasing your aperture size. When you are decreasing your aperture size, that means you are allowing the beams to not to go far from the optic axis. That means your let's say this is your aperture, and you are not allowing all these rays to come back again and then create an angle. Rather, you are allowing all the rays which are close to the optic axis, so that this angle is less than this angle. So that is how you increase your depth of field. Okay, by and if you want to increase the depth of field, your spot size should be also increased, right? And to finally coming to the detector system, there are different kinds of detectors are there associated with SEM. One is ET detector, which is known as Everhart-Thornley detector. This is a detector which collects both AC plus BAC. Generally, there is a misconception that ET detector is collecting only AC, though it is primarily used due to the experimental dependency of AC on this ET detector. But both it can collect. ET positive will mostly collect the AC. ET negative detector, negative positive means if the detector is positively biased, it will collect the secondary electron signal. If the detector is negatively biased, then it will also collect backscattered signal, not secondary electron signal. And this is a TTL detector, that means through the lens detector. So this detector is placed, so this is the objective lens. When the beam comes, right, so these detectors are placed like this here. So this is what called, this is the lens, so this is called through the lens detector. So somewhat the schematic should be somewhat like this. So these are the through the lens detector. There are also detector for dedicated backscatter to collect backscattered electrons. So similarly, backscattered electron to secondary electron conversion detector is also there. 5 secondary electron conversion BAC to SE conversion detectors are there, because there is a secondary electron signal which is secondary electron third. We have discussed this in the previous class, which will come from the backscattered electron. When the backscattered electron, let's say this is my sample, okay, backscattered electron goes and hit the lens here. This is the lens, let's say backscattered, this is a B, backscattered electron goes and hit it. Then in this process, what will happen? Some electrons will lose its energy and then they will convert to AC. These are the, then for that some detector are made, so that is what called as backscatter to secondary electron conversion detector. And the final one, solid state diode detector, which is most nowadays in all modern SEM solid state diode detector, mostly they are lithium doped silicon detector. Why silicon is used? Because silicon is a semiconductor material, and this, the mechanism of this detector is to create electron hole pairs. Okay, when electron hole pairs are created in a semiconductor, then by applying negative bias or positive bias, we separate them, and finally we will get the electron signal. Then contrast comes. Contrast, we know that one is compositional contrast, another one is topological contrast. This compositional contrast comes due to the difference in atomic variation, and the topographical contrast generally comes from the shape, size, and the the position of the sample as compared to the plane of optimum focus, right? So in the contrast here, in case of SEM, the contrast is defined as, let's say, an earlier case we are talking about change in current intensity, right? In light optics, here we are talking about signals that we are getting. In SEM we will be talking about signals that we are getting from our specimen. Let's say I have two types of signal, S1 and S2, and S1 let's say S2 is greater than S1. So in this case the contrast will be S2 minus S1 by S2. Right. So earlier case we are talking about the contrast in terms of intensity. Now we will talk in ACM we talk about the contrast in terms of signals that we are getting. And here the X-ray radiation, the secondary electron also comes. X-ray radiation we'll study in brief when the X-ray radiation comes. Just I'm telling you just in short that let's say this is an outer cell and this is an inner cell electron of an atom. One incident energy when it comes, a strong beam, electron beam comes with high incident energy, high energy. One incident electron beam comes and somehow it gives enough energy so that this electron, okay, this inner cell electron, I'm not talking about this electron, in this inner cell electron, this gets sufficient energy and this inner cell electron goes out. So the moment it goes out, what will happen here? There will be a vacancy formation happen here, right? And since this is the inner cell electron, it is more closely bound to the atom here. Since there is a vacancy and this is a outer cell electron, it will immediately fall on to fill this vacancy, this outer cell electron. Now, since its energy is high, it is coming to this energy, the inner cell electron, to fill the vacancy created by this inner cell electron. This is high energy, this is low energy. Since from high energy to low energy, this electron is coming to fill the vacancy created by this electron. So there will be some kind of radiation coming. So this radiation is X-ray characteristic radiation. Okay, so there are different types of radiation are there. One is characteristics X-ray, another one is we will study which is white radiation. So white radiation we will study what is that in X-ray diffraction and do the in subsequent classes. But this radiation which is coming, this is X-ray characteristics radiation. So two types of radiation generally comes out. So to capture and remember the energy of this cell, it is fixed. The energy, let's say I am talking about K cell, this is L cell. So the energy of a particular material for K cell, it is fixed. The energy of a particular of L cell for a particular material, it is also fixed. So the energy difference between L and K are also fixed. So that is why when we want to do an EDS, that is energy dispersive spectroscopy, and we want to capture this energy, what is the amount of energy that we are getting after the bombardment of this incident electron beam on our material, that is how we so this characteristic radiation will be having some fixed energy, right? And this fixed energy when we capture it in EDS, energy dispersive spectroscopy, right? And same thing, little bit modification of this X-ray radiation generation is Auger electron. What is Auger electron? Let's say this is my nucleus and around this some electrons are there, okay, and one energy comes, incident electron energy comes, gives this one an energy, right, and this goes out, and immediately this will try to come and fill its, so here a vacancy happened and this electron, let's say I am naming it electron 1, will try to fill the vacancy created by electron 2, right? So and some radiation now due to this, so this radiation goes out. Now this radiation is also having some amount of energy, right? This radiation, so this radiation, if that gives some amount of energy to this outer cell electron, which I am denoting by an arrow mark here, then this will also get some energy, this outer cell electron. Now this outer cell electron, if it goes out, this is known as Auger electron. Okay, so when this extra amount of energy which is came out during the jump from L cell to, let's say, K cell, and that energy is used by another electron, another outer cell electron, which is weakly bound to the atomic nucleus, and that electron goes out, then that is what called as Auger electron. Okay, so this is the definition. This is how we see we do the Auger electron spectroscopy, but generally in ACM scanning electron microscopy we are heavily dependent on EDS, energy dispersive spectroscopy, where we capture the particular energy. How those energies are coming out? Those are coming out by X-ray radiation. Okay, so that is the end of all concept. So we will see now a few questions. So yeah, we'll go through a few questions now, practice questions. So the question one is, an electron beam of brightness 10 to the power 10 ampere meter to the power minus 2 ampere per meter square into steradian is focused to a spot of diameter 100 nanometer at the specimen. What is the current density ampere per meter centimeter square within the spot? Take the convergence angle to be 0.04. Okay, so we'll solve these questions. So here some of the given answers are brightness, some of the given parameters are brightness. So the brightness, if I am talking about, okay, 10 to the power 10, right? And yeah, and another, it is asking current density. Okay, spot diameter it has given, and convergence angle it has given. So convergence angle, if I am talking alpha 0.04 radian. So yeah, can anyone solve this question? Just try to solve it for 1 minute, then I will solve it. So these are the given brightness, convergence angle it is asking, and the probe diameter it has also given, and it is asking what is the current density. Okay, so we'll solve it now. Here there is an additional information which is given by spot diameter, that is why I did not write it here. So the spot diameter is additional information that we don't have to worry about. Okay, so because we know that brightness is current density per unit solid angle, right? And the solid angle is made by convergence angle. If you rotate the convergence angle in 3 dimension, so that is the that is the unit solid angle. So here let's say I'm talking about JC, so solid angle is given by and alpha, right? So solid angle is alpha, the convergence angle. Okay, so alpha square, this is the formula. So they have asked what is the current density in this case directly. That means JC will be equal to beta, which is brightness, into pi.
Sir, B is the answer, sir.
Which one?
B, sir.
B is the answer. Oh, okay, let me check. Beta pi into alpha square. So here beta is 10 to the power 10. Pi is this much, alpha is 0.04. Okay, I don't, let me check on the calculator. So pi into 0.04. Okay, 0.4 square, sorry, right, 0.4 square. No, B is not the answer. The answer is coming 5.02 into 10 to the power minus 3, 5.0265 into 10 to the power minus 3 into 10 to the power 10. So it will be 5 into 10 to the power 7. A is the answer. Just check your calculation. Somewhere you might have missed something. So A is the answer. So here 0.04 square is there. Just take that into calculation. Okay. So yeah, A will be the answer in this case. Nothing but just a formula for brightness. Always remember this formula for the brightness, because it will help you solve many conceptual questions also, because you don't need to remember all the formula. Based on this formula you can derive many other formula like Gaussian probe diameter, the convergence angle. So this is a good concept to remember, the brightness. The brightness is flux for unit solid angle. Okay, and that solid angle is nothing but the 3-dimensional rotation of the convergence angle. Okay, so this is another question that this is a conceptual question. Energy of Auger peak compared to the equivalent X-ray peak will be higher, lower, or same? Any guess? We just covered the Auger peak, Auger electron.
Lower, sir.
Uh, which one? I cannot hear you properly.
B. Lower.
Yes, it is B, lower, because X-rays when they are emitted means after the emission of the X-ray, the fraction of that energy is transferred to an electron. Then that electron, if if that energy crosses its work function, then the electron goes out of the outer cell. So that means X-ray, the fraction of X-ray energy is used to emit the Auger electron. So that means the Auger peak that we are getting will be definitely lower than the X-ray peak. That's the correct answer. Then the next question is, which of the following materials is not commonly used as a coating for SEM samples to enhance conductivity and minimize charging effect? If you remember, we have I have told you in the last class that for metallic material the charging will not happen, but for metallic is a conductive material, but the non-conductive material we generally deposit something on our sample. So that deposition is, I have told one option I have told from here, that is made up of AU. So based on our requirement, we do the deposition of one. Ideally, the deposition should be of the thickness of 1 to 2 nanometer, but that is very difficult to achieve. So sometimes 1 to 10 or sometimes even 20 nanometer of gold we deposit, right? So that the accumulation of the electron onto the surface of the material should not be there. So definitely gold is not an answer. So rest 3 which you can tell. Not used here, not commonly used. Which one? Here, that one hint I will give here. This is the hint to enhance conductivity.
Platinum.
No. Platinum is an excellent conductor of it carries current.
Silicon, sir.
Yes, silicon is the answer, because platinum is a metal, it's a metal, and it is also a good conductor of electricity. Carbon is also a very good conductor of electricity. Silicon, why? Because silicon is a semiconductor. So so semiconductor means we have to give some, I think it is 3.6 electron volt, the gap between the conduction band and valence band. So that is why silicon is the correct answer. Like not commonly used. All the other three, mostly gold is used. Carbon, platinum are also used according to the requirement. Yes, which parameter has the most significant influence on the depth of field in an SEM image? We just discussed depth of field and depth. I told that in SEM sometimes people in some textbook the depth of this field is also written as depth of focus, right? In case of SEM only. So which parameter has the most significant influence? Accelerating voltage, spot size, working distance, and magnification. So anyone remembers? Okay, so this answer will
Working distance.
Which one?
C, sir. Working distance.
Working distance. No, you can just tell it by the formula that I have given.
Accelerating voltage.
Accelerating, no. No.
Sir, magnification.
No. The formula is, it is somewhat close to I told, right? And this is what? The spot size. Right? This thing, this one. Okay, so this will have most, so this is the formula, D is equal to 2R by alpha, right? So spot size is the correct answer. You just have to remember this formula, means D is equal to 2R by alpha. You should remember the figure, understand the figure, but this, yeah, what are the significance of alpha and why the alpha and R, these are the two terminology, how do they affect this D, you should remember that thing. So R is the spot size here, okay. That is the most, it will have the most significant influence. Others will also influence, like R is also associated with magnification, if you tell. Then alpha is also associated with some other working distance. So in that case they will also affect, but when it says that most significant influence, you should consider this formula, which is D is equal to 2R by alpha. Yeah, so how reducing the probe size will affect beam current in SEM? Yeah, can anyone answer? It is a simple question. I think in this lecture we have discussed it many times. It is related to the aperture. I'll give you a hint. This is related to the aperture of the aperture which is used in the SEM, like increasing and decreasing aperture. So yeah,
Reduce A.
reduce A, yes. So that is the correct answer. Reduce probe size means the beam current will also be reducing. Okay, so probe is nothing but the incident electron which are falling onto the specimen. If we are decreasing by putting an aperture here instead of a bigger aperture, then effectively we are blocking many signals from here in this region. So let's say this is my sample. Okay, so that means it will reduce. Correct answer. And yeah, which of the following option is correct? Can anyone tell? Before this, I actually okay, yeah, tell this one, then I'll tell another thing. Okay, I'll just tell then. I think I made a mistake in the last class. Actually, many of you were correct. In the last class, there was a question in the last, I think question number 12, which was which one is used for grain size grain orientation in the SEM. I think many of you have told that the BSE is used, and that was the correct answer, but I told that AC was used, which was not the correct answer. So that was a mistake from my side. I apologize for that. BSE is used for the grain size orientation. That question was, I think which one is used for the measurement of grain orientation. Okay, and the BSE signal is used for the measurement of grain orientation. So yeah, so just to make sure that you can, I will upload that slide also in this after the completion of this tutorial. But yeah, that was a mistake from my side. So SE is not used. BSE is used always for grain size orientation. And I told that BSE was only BSE is only used for grain orientation relationship, not only in relationship but also to see what is the orientation of a single grain. For that also backscattered electron is used. Okay, yeah, so now you can say which of the following option is correct: secondary electron, backscattered electron, X-ray, Auger electron, imaging, crystal structure, compositional analysis, detection of very light element.
A is correct. A.
Yes, sir.
A is the correct answer.
So secondary electron is used for imaging, backscattered electron for crystal structure, X-ray for compositional analysis, that means phase identification. We'll see it in X-ray XRD how the phase identification happens, and Auger electrons are used for detection of very light element. Okay, that's the A is the correct answer. Yeah, so what is the effect of reducing the accelerating voltage in SEM imaging on non-conductive sample? So the question is, I'll rephrase the question for you to understand. The question is what happens when we reduce the accelerating voltage on a non-conductive sample? That's all. What will happen?
B, sir.
Which one?
B, sir. B.
B.
B, decrease.
Yes. So that
Decrease the charge.
So when many times what will happen if we are going with a polymer sample or we are going with a ceramic sample which is non-conductive in nature, we do it with an AC image. That means AC, secondary electron imaging, we do it at a lower accelerating voltage, and BSE if we do, and if we go to higher magnification, there are lot of charging will happen. That means for the first scan, when you see, let's say this is my sample, for the first scan you have an artifact here, right? So when the scan will happen and the charging takes place, so this is your sample at the first look, but when the scan happens, this will be like this. It will start to distort, so you will know that the charging is happening. And so this is, and I am talking about live view, not in after taking image. This is the, let's say, first second you are seeing, and this is the second you are viewing. If you go further, then this might be like this. This was a point in first section. In first second, let's say this is nth second you are viewing so this is also a live view, so it will further increase. So that is what charging is, that in that case we reduce the accelerating voltage. Okay, next question is, when adjusting the condenser current in SEM, what is the relationship between condenser and the final probe current? Can anyone answer?
Sir, B, sir.
Directly proportional, directly. B.
Yes, that is the correct answer. So the condenser current is generally used to adjust the intensity of the electron beam. Okay, so that means higher intensity electron beam finally increases the final probe current. So they are directly proportional to each other. So the next question, yeah, this is straight question. For thermionic emission, which of the following factors affect the efficiency of the electron emission for a material? Material's density, material's thermal conductivity, material's work function, material's tensile strength. So thermionic emission means I am talking about an electron gun here. So electrons are coming out, and thermionic emission means temperature is greater than 2700 Kelvin. Electrons are coming out. So what will happen in that case? Which is the factor that will affect?
Work function.
Yes, the answer is work function. Why work function? Because work function of a material generally represents the minimum amount of energy required for an electron to escape the surface. So that's what work function generally means. Lower work function, if say my material has a lower work function, then it requires less energy. Means the moment I hit the my material beyond 2700 Kelvin, it will immediately go out. And yes, the coefficient of spherical aberration increases by 1%. What could be the percentage change in minimum probe size? If anyone remembers, I have told one in today's class that there was one important expression for D minimum. You can apply that and answer. If the spherical aberration coefficient increases by 1%,
It is A.
yes, A is the answer, because spherical aberration coefficient varies by 1 to the 1 by 4, right? So that is what how the spherical aberration coefficient varies to the D minimum. So answer is A. So we'll go through, what is the time now? 8:05. We'll go through 5 more questions, conceptual, quickly. So to obtain higher convergence angle, what is needed? Larger final aperture or lower working distance, smaller final aperture or higher working distance, independent of aperture size and working distance. So in ACM examination, most of the conceptual questions will come in this way, like convergence angle, probe size. So you should be able to always draw the diagram, and then you will be able to get the correct answer. So I am getting, so let's say I am talking about higher convergence angle. That means my alphas would be higher. Let's say my sample is this much. Okay. So larger final aperture. If my final aperture is larger, let's say like this, then the convergence angle, effectively this is my convergence angle, right? Alpha P. So if I am getting larger aperture or lower working distance, this working distance I will even try to lower this one, then I will get higher convergence angle. Smaller final aperture means, let's say you are keeping your sample or higher working distance, let's say we'll see this case. So you will never get a higher aperture angle, convergence angle. Okay, always more. The smaller final aperture means we will get higher depth of focus or depth of field. Okay, so similar for higher working distance also, but in this case the larger final aperture and the lower working distance will give you higher convergence angle. And the more higher convergence angle means, generally this is not needed, because more higher convergence angle means spherical aberration will also take place higher. So generally this is not the case, but yeah, from questions perspective you can draw the diagram. Yeah, so in SEM, to produce better resolution, probe size needs to be, this is a straightforward question. This is related to the demagnification. I would give a hint. So any guess?
Probe size should be decreased.
Yes, so probe size should be decreased. It is related to the demagnification. So the less probe size you will have, the more your better resolution you will get from your image. Then yeah, which one among the statement is false when working distance is increased? So when working distance is increased, what will happen? It gives less magnification, degrades the resolution, produces large spot size, reduces the scan length. So you remember the scan length I have told, so you can try to draw the diagram and see. The scan length means I have drawn it in terms of tilted specimen, right? So the answer I am telling that this is D. D is the false one. It does not reduce. So here you have to see whether the question is about true or false. Since they have asked about false statement, it definitely does not reduce the scan length. It increases the scan length, right? So that is why the magnification will also go down. Okay, magnification goes down. It is correct. Degrades the resolution. It is also correct because probe size will be higher. Produces large spot size. It is also correct. Then reduces the scan length. This is not correct. And the penultimate question is interaction volume increases the spatial volume. What is the correct answer? The spatial resolution. This is related to when I was talking about the electron beam and specimen interaction. When I was talking about that our electron probe size is 2 nanometer. Then why we need to go for the simulation? And why we need to consider the interaction volume? From that perspective you can think.
A is the answer.
A is the answer. A.
Interaction volume increases. No, the resolution I am talking about, not the information that we will get. B is the answer. Okay. Interaction volume, when it increases, I am talking about the resolution, not the amount of information that we will collect. Of course, the amount of information that we will collect will be large. That increases. But the resolution means the electron which you will be having a particular energy, right? So the energy graph, if you will see, it will be like this. So the loss of the energy for a particular beam of electrons will happen, and if that happens, then the resolution will decrease. You might be getting a good amount of area to scan, but I'm talking about the resolution. So resolution I'm talking, we have talked like 2 nanometer this thing is coming, right? 2 nanometer beam is coming. So 2 nanometer means effectively I'm getting information from this using this 2 nanometer probe. But what is happening now? All of these electrons are coming out, whether it's AC and BAC, all of them are coming out. So effectively I'm getting signal from a broad range of energy. If I am getting signal from a broad range of energy, my resolution is decreasing. And the final question is, what information can be obtained from brighter region in BAC image? This is related to, I'll give you a hint, compositional contrast.
B.
B, yes.
B, sir, B.
That is the correct answer. It indicates element with higher atomic number. Okay. So yeah. So that concludes our session.